Somewhere out there tonight, closer than you might expect, a small rocky world circles a dim red star in the darkness between here and there. This world, known as Proxima Centauri b, drifts through space just over 4 light-years away from where you are resting right now. Close enough that the light leaving its surface tonight will reach Earth before this decade ends. The star it orbits, Proxima Centauri, is the nearest star to our own Sun. A faint red ember that our ancestors never knew existed because human eyes cannot see its glow without a telescope. And around that small, quiet star, a planet roughly the size of Earth moves through the habitable zone, the region where temperatures might allow liquid water to pool on a rocky surface. This is where our slow journey begins tonight. Among the worlds that might harbor the conditions for life as we understand it. Planets scattered across the galaxy in zones where liquid water could theoretically exist. These are not imaginary places invented for stories. They are real worlds detected by real instruments, their presence confirmed through careful observation across the distances that separate us from them. Some orbit stars so different from our Sun that the light falling on their surfaces would appear deep red rather than golden yellow. Others circle stars remarkably similar to ours, receiving warmth and radiation in quantities not so different from what Earth receives from the Sun each day. You are listening to the Drowsy Astronaut, and tonight we drift together through 100 remarkable facts about exoplanets, the worlds that orbit stars beyond our own solar system. This is a slow, unhurried journey designed for late nights when curiosity and rest can exist in the same quiet space. If you enjoy these calm explorations of the cosmos, consider leaving a comment sharing where you are listening from tonight. We'll start with the one that fascinates me most, a distant world where sunrise may never come and sunset may never end. Proxima Centauri b orbits its star at a distance of roughly 7 million kilometers, which sounds like an enormous number until you realize that Earth orbits the Sun at 150 million kilometers. This close orbit means the planet completes 1 full year in just 11 Earth days, racing around its star while our own world barely moves through its much larger path. The star itself, Proxima Centauri, produces far less heat and light than our Sun, which is why a planet must orbit so closely to receive enough warmth for liquid water. At this intimate distance, the gravitational relationship between star and planet has almost certainly locked the world into a fixed orientation, one face forever turned toward the dim red light. The side facing the star experiences permanent day, a hemisphere where the red sun never sets and never moves across the sky, fixed in place like a painting on the ceiling of an enormous room. The opposite hemisphere knows only permanent night, a frozen expanse where starlight provides the only illumination across landscapes that have never known dawn. Between these two extremes, a ring of perpetual twilight circles the entire planet, a zone where the star hangs forever on the horizon, half risen or half set depending on where you stand. Scientists believe this twilight zone might offer the most comfortable conditions for life. With moderate temperatures and the gentle glow of an eternal sunset, painting everything in shades of deep red, and orange. The TRAPPIST-1 system presents an even more remarkable arrangement. 7 Earth-sized planets orbiting a single small star in a configuration so compact it defies our solar system's sense of scale. All 7 of these worlds orbit closer to their star than Mercury orbits our Sun, yet 3 of them sit comfortably within the habitable zone where liquid water could potentially exist. The star at the center, TRAPPIST-1, is what astronomers call an ultra-cool red dwarf, producing just a tiny fraction of the light and heat that our Sun generates. This dim output means planets must huddle close to receive adequate warmth, creating a system where neighboring worlds appear as large disks in each other's skies, rather than distant points of light. Standing on the surface of TRAPPIST-1e, one of the potentially habitable worlds, you would see sibling planets crossing overhead, their surfaces visible in enough detail to distinguish basic features with the unaided eye. The innermost planet completes an orbit in just 1.5 Earth days, racing around the star while you watch from your more distant vantage point on world number 5. These 7 planets are locked into what scientists call an orbital resonance, their periods related by precise mathematical ratios that keep them stable over billions of years. The system resembles a cosmic clockwork mechanism, each world influencing the others through gravity, while maintaining the delicate balance that prevents collisions or ejections. The discovery of water vapor in the atmosphere of K2-18b marked a turning point in our ability to study potentially habitable worlds in genuine chemical detail. This planet, larger than Earth but smaller than Neptune, orbits within the habitable zone of its red dwarf star, roughly 120 light-years from our solar system. The James Webb Space Telescope detected not only water vapor in its atmosphere, but also hints of carbon dioxide and possibly methane, molecules that interact with each other in ways scientists are still working to understand. Most intriguingly, the observations showed tentative signs of dimethyl sulfide, a molecule that on Earth is produced primarily by living organisms, particularly phytoplankton in the oceans. The dimethyl sulfide detection remains uncertain and requires further observation to confirm, but the mere possibility has sparked intense discussion about what such a signature might mean. If future observations strengthen the detection, scientists would need to determine whether the molecule could be produced by non-biological chemistry under the conditions present on K2-18b. The planet itself may be a type of world completely absent from our solar system, a water world covered by deep oceans beneath a thick hydrogen-rich atmosphere. Light from its star filters through this atmosphere, carrying chemical fingerprints that our telescopes can read across the vast gulf of space, separating us from this distant shore. Kepler 442b sits among the most Earth-like worlds ever discovered, earning an Earth similarity index of 0.84 out of a possible 1.0. This number attempts to capture how closely a planet resembles Earth in terms of size, temperature, and the type of star it orbits, providing a rough comparison even though many important factors remain unknown. The planet orbits an orange dwarf star, slightly cooler than our Sun, receiving about 70% as much light as Earth receives from its yellow star. A year on Kepler 442b lasts about 112 Earth days, meaning seasons would cycle more quickly if the planet experiences seasonal variation at all. The star itself is older than our Sun by approximately 2 billion years, meaning this system had far more time for any biological processes to potentially develop and evolve. Of course, many factors beyond temperature determine whether life could arise, including the presence of an atmosphere, the existence of a magnetic field, and the availability of the chemical building blocks that biology requires. Kepler 442b orbits far enough from Earth that detailed study of its atmosphere remains extremely challenging with current technology, though future telescopes may eventually reveal more about this distant cousin. For now, it represents one of the most promising candidates in a growing catalogue of potentially habitable worlds scattered across the Milky Way galaxy. LHS 1140b offers certain advantages over the more famous Proxima Centauri b, particularly in terms of the behavior of its host star and the radiation environment the planet experiences. Red dwarf stars like Proxima Centauri often produce powerful flares that could strip away atmospheres and bathe planetary surfaces in harmful radiation over time. The star LHS 1140 appears to be quieter and more stable, producing fewer energetic outbursts that might threaten any atmosphere a planet managed to develop and retain. This relative calm makes LHS 1140b a compelling target for future atmospheric studies, as any atmosphere present has better odds of surviving long enough to be detected. The planet itself is a super-Earth, larger and more massive than our home world, which means its stronger gravity could help it hold on to atmospheric gases more effectively. It orbits in the habitable zone of its star, receiving an amount of energy compatible with liquid water existing on its surface under the right atmospheric conditions. At roughly 40 light-years away, it sits close enough for detailed study, with next-generation telescopes designed specifically to characterize the atmospheres of small rocky worlds. The combination of a quiet host star, appropriate orbital distance, and relatively close proximity to Earth makes this world one of the most important targets in the search for habitable environments beyond our solar system. The habitable zone around any star is not a fixed eternal region, but shifts and changes as the star itself ages and evolves over billions of years. Young stars often burn more energetically than they will in later life, pushing the habitable zone outward before it gradually migrates inward as the star settles into steady, middle-aged fusion. Our own Sun has brightened by roughly 30% since the solar system formed, meaning Earth was near the outer edge of the habitable zone early in its history. Planets that currently sit outside a star's habitable zone may have experienced temperate conditions billions of years ago, potentially hosting life that has since perished as conditions changed. Similarly, worlds currently frozen and inhospitable may eventually warm as their stars brighten with age, though the timescales involved stretch across billions of years of patient stellar evolution. This changing nature of habitability adds complexity to the search for life, reminding us that conditions we observe today represent just one snapshot in a very long cosmic history. A planet that appears barren now might have supported oceans in its distant past, while a currently frozen world might eventually thaw into habitability in the far future. The universe operates on timescales so vast that entire chapters of planetary history can unfold while we observe only a single frozen moment. TOI 700 represents a particularly exciting discovery from the TESS mission, an Earth-sized planet orbiting within the habitable zone of a nearby red dwarf star, roughly 100 light-years from our position. Unlike many habitable zone candidates that turn out to be significantly larger than Earth, this world measures almost exactly Earth's size, making it one of the best analogues to our home planet discovered to date. The TESS spacecraft, designed to survey the nearest and brightest stars for transiting planets, detected the slight dimming caused by TOI 700d passing between its star and our line of sight. Follow-up observations confirmed the planet's existence and refined measurements of its size and orbital characteristics with increasing precision. The system contains at least 3 other planets in addition to this habitable zone world, all orbiting the same small red star in a compact configuration, somewhat reminiscent of the TRAPPIST-1 arrangement. TOI 700d completes one orbit in approximately 37 Earth days, receiving about 86% of the energy that Earth receives from our Sun. Scientists have modeled various possible atmospheric compositions to predict what surface conditions might be like, though actual atmospheric observations remain beyond current capabilities for such a small world. As technology improves in coming decades, this planet will likely become a prime target for instruments designed to study the atmospheres of Earth-sized worlds in habitable zones. Kepler 452b has sometimes been called Earth's older cousin, an exoplanet that orbits a Sun-like star at a distance remarkably similar to Earth's orbital radius around our own Sun. The planet is larger than Earth, roughly 60% wider in diameter, which might make it a super-Earth with considerably stronger surface gravity. Its star is a G-type star like our Sun, though approximately 6 billion years old, compared to our Sun's 4.5 billion years of age. This additional age means the star has brightened somewhat over time, possibly pushing the habitable zone outward and changing conditions on any planets that formed in what was once a temperate region. A year on Kepler 452b lasts roughly 385 Earth days, almost identical to our own year, which creates an oddly familiar rhythm for such a distant and alien world. The planet orbits approximately 1,400 light-years from Earth, far enough that light leaving its surface tonight will not arrive here for more than a millennium of patient travel. We cannot yet determine whether this world has an atmosphere, oceans, or any features that might make it truly Earth-like beneath its familiar orbital parameters. The planet serves as a reminder that similarity in some respects does not guarantee similarity in all respects, and that true understanding requires observations we cannot yet perform from this great distance. The first part of our journey through 100 exoplanet facts has explored the worlds that orbit within the special regions around their stars, where liquid water might exist on rocky surfaces. These habitable zone planets represent the places where life as we understand it has the best chance of finding conditions it might recognize as welcoming. Yet distance and technology still limit what we can learn about most of these worlds, leaving questions unanswered that future generations of astronomers will work to resolve. The search continues with new telescopes and new missions, each observation bringing us closer to understanding whether any of these distant worlds might truly harbor something alive. The James Webb Space Telescope changed everything when it began returning data in the summer of 2022, revealing exoplanet atmospheres in detail that previous instruments could only dream about. This observatory, positioned nearly 1 million miles from Earth at a gravitationally stable point called L2, carries a mirror over 6 meters across that gathers light with extraordinary sensitivity. Its infrared vision pierces through the kinds of obscuring material that block visible light, revealing thermal signatures and molecular fingerprints that other telescopes cannot detect. Within months of beginning science operations, Webb began rewriting our understanding of what exoplanet atmospheres contain and how those atmospheres behave. The first definitive detection of carbon dioxide in any exoplanet atmosphere came from Webb's observations of a world called WSP-39b, a hot gas giant orbiting close to its star. Previous telescopes had detected other molecules in exoplanet atmospheres, including water vapor and sodium. But carbon dioxide had remained elusive until Webb turned its powerful instruments toward this target. The detection appeared as a distinctive absorption feature in the planet's transmission spectrum, a dip at precisely the wavelength where carbon dioxide absorbs infrared light passing through an atmosphere. This measurement demonstrated that Webb could identify specific molecules in exoplanet atmospheres with confidence, opening doors to far more detailed chemical analysis of distant worlds. WSP-39b also yielded the first detection of sulfur dioxide in any exoplanet atmosphere, a discovery that revealed active chemistry driven by the intense light of the nearby host star. This molecule forms when starlight breaks apart other sulfur-containing compounds high in the atmosphere, driving reactions that create new substances from the raw materials present. The process, called photochemistry, plays important roles in planetary atmospheres throughout the universe, including our own Earth's ozone layer formation. Finding evidence of photochemistry at work in an exoplanet atmosphere confirmed that these distant worlds experience many of the same physical and chemical processes that shape atmospheres closer to home. The presence of sulfur dioxide also tells scientists about the overall composition and structure of the atmosphere, since this molecule only forms under certain conditions of temperature, pressure, and available raw materials. WSP-39b orbits so close to its star that its atmosphere reaches temperatures exceeding 1,000 degrees, creating conditions very different from any planet in our solar system. At these extreme temperatures, molecules behave in unusual ways, remaining gaseous at concentrations that would condense into clouds or liquids under cooler conditions. Webb's ability to detect and measure these molecules provides a window into atmospheric chemistry under conditions we cannot replicate in laboratories on Earth. The TRAPPIST-1 system has become a primary target for Webb's exoplanet observations, with multiple dedicated programs studying the 7 Earth-sized worlds that orbit this nearby red dwarf star. Early observations focused on the 2 innermost planets, TRAPPIST-1b and TRAPPIST-1c, searching for signs of atmospheres around these scorched and likely tidally locked worlds. Initial results suggested that TRAPPIST-1b probably lacks a substantial atmosphere, with no clear signs of the thick carbon dioxide envelope that some models had predicted might be present. These findings, while perhaps disappointing for hopes of habitability on this particular world, demonstrate Webb's capability to make meaningful measurements of rocky planet atmospheres. The outer planets of the TRAPPIST-1 system remain objects of intense interest, particularly those orbiting within the habitable zone where temperatures might permit liquid water. Webb has dedicated observation time scheduled for these worlds, searching for atmospheric signatures that could indicate conditions favorable to life as we understand it. The measurements are extraordinarily challenging, requiring detection of subtle changes in starlight as it filters through the thin atmospheric layer surrounding an Earth-sized planet. Even Webb's powerful capabilities face difficulties extracting these faint signals from the noise. But each observation adds to our understanding of what these tantalizing worlds might actually be like. LHS 475b became one of the first rocky planets whose existence was confirmed directly through Webb observations, demonstrating the telescope's ability to verify and characterize small worlds discovered by other instruments. The TESS mission had flagged this system as potentially hosting a transiting planet, but confirmation required the precise measurements that only Webb could provide. The observations not only confirmed that the planet exists, but also constrained its size to match Earth's diameter within a few percent, making it one of the smallest exoplanets ever studied in such detail. Webb found no evidence of a thick atmosphere surrounding this world, though a thin atmosphere, or one with unexpected composition, might still escape detection. The capability to study rocky planets individually, rather than merely detecting them as statistical blips in survey data, represents a fundamental shift in exoplanet science enabled by Webb's launch. Previous space telescopes like Kepler excelled at finding planets by the thousands, but could reveal little about any individual world beyond basic size and orbital information. Webb can examine planets one at a time, studying their atmospheres, temperatures, and chemical compositions with unprecedented precision and sensitivity. This transition from discovery to characterization marks a new era in which exoplanets transform from dots on charts into actual places with measurable properties and conditions. K2-18b drew intense scientific and public attention when Webb observations revealed not only water vapor, but also potential signs of molecules associated with biological activity on Earth. The tentative detection of dimethyl sulfide sparked cautious excitement, as this molecule is produced primarily by marine life in Earth's oceans, rather than by known non-biological chemistry. Scientists emphasized repeatedly that the detection remains uncertain and that many alternative explanations exist for the observed spectral features. Further observations with Webb and future telescopes will be needed to determine whether the detection is real, and, if so, what processes might create this molecule in an alien ocean world's atmosphere. The planet itself represents a category of world that does not exist in our solar system, larger than Earth, but smaller than Neptune, possibly covered by deep oceans beneath a thick hydrogen-rich atmosphere. Such worlds, sometimes called Hycean planets, offer potentially habitable environments quite different from Earth's surface-dwelling life, but perhaps suitable for organisms adapted to aquatic existence. The concept remains theoretical, as we have never directly observed the surface or depths of any such world. But the chemistry Webb can detect provides tantalizing hints about conditions far below the visible atmosphere. K2-18b will remain a priority target for continued observation as scientists work to understand what this strange and distant world might actually be like. Webb's coronagraph instruments allow it to block the overwhelming glare of stars, revealing faint objects orbiting nearby that would otherwise be completely invisible against the stellar brightness. This capability has produced direct images of young gas giant planets still glowing with the heat of their formation, their light separated from their host stars through sophisticated optical manipulation. The young brown dwarf companion VHS 1256b revealed clouds made of silicate particles, essentially rock vapor suspended in an atmosphere hot enough to keep stone in gaseous form. Such direct imaging complements transit observations by studying different types of systems and different regions of planetary atmospheres. The ability to photograph exoplanets directly opens possibilities for studying worlds that never transit across their stars from our perspective, vastly expanding the types of systems we can examine in detail. Most planets discovered through transit methods orbit with their orbital planes aligned nearly edge-on to our line of sight. But this represents only a small fraction of all possible orbital orientations. Direct imaging can study planets orbiting at any angle, revealing the full three-dimensional architecture of planetary systems, rather than the subset that happen to transit. Combined with spectroscopy, direct images can reveal atmospheric composition for planets that we can actually see as resolved points of light. WSP-96b provided one of Webb's most beautiful early results, a transmission spectrum showing clear evidence of water vapor in the atmosphere, with distinct absorption features uncontaminated by clouds. Many exoplanet atmospheres contain high-altitude hazes or clouds that mute spectral features, making molecular identification difficult or impossible even with sensitive instruments. WSP-96b appears to have relatively clear skies, allowing starlight to pass through deeper atmospheric layers, where water molecules absorb specific wavelengths with sharp, identifiable precision. The resulting spectrum became an iconic early image from Webb, demonstrating the telescope's capabilities while revealing genuine scientific insights about this distant gas giant. The transition from detecting that exoplanets exist to understanding what they are actually like has accelerated dramatically since Webb began operations, with each observation adding details to our emerging picture of planetary diversity. Previous generations of astronomers wondered whether planets existed around other stars at all, a question definitively answered only in the 1990s. The current generation can ask far more specific questions about atmospheric composition, temperature structure, weather patterns, and chemical processes operating on individual worlds. Future generations will likely ask about geology, ocean circulation, and perhaps even biological activity on worlds that today we can barely characterize at all. The second part of our journey has explored how new eyes in space have transformed exoplanet science from catalog building to world understanding in just the past few years. The James Webb Space Telescope represents the cutting edge of what humanity can currently achieve in studying distant planetary systems. But it is not the final word. Future observatories planned for the coming decades will push these capabilities even further, eventually enabling study of Earth-like atmospheres around Sun-like stars. The discoveries revealed so far only hint at what remains to be found as our technological reach continues extending outward into the cosmos. Some worlds burn with heat so extreme that our everyday understanding of temperature and matter begins to break down entirely under conditions no earthbound experience could prepare us to imagine. The hottest known exoplanet, Kelt 9b, reaches temperatures exceeding 4,600 Kelvin on its dayside, hotter than the surfaces of most stars in the galaxy. At these extraordinary temperatures, molecules that we think of as stable and permanent simply cannot exist, torn apart by thermal energy into their constituent atoms. Iron, titanium, and other metals that we associate with solid objects exist as gases in this world's atmosphere, flowing like weather patterns across an alien sky. The star that Kelt 9b orbits is itself unusual, a hot blue star that pours out far more radiation than our yellow sun produces, heating its close companion to these stellar temperatures. The planet orbits so near to this blazing star that it completes one full year in just 36 hours, racing around its orbit while being continuously blasted by intense radiation. Ultraviolet light and stellar wind are gradually stripping away the planet's atmosphere, creating a tail of escaping gas that trails behind the world like a comet's tail stretching away from the sun. Scientists estimate that this atmospheric loss will eventually leave behind only the dense core, assuming the planet survives long enough without being consumed entirely by its expanding host star. JWST-76b has captured public imagination through its iron rain, a phenomenon so alien that it sounds like something invented for science fiction rather than observed through actual scientific measurement. The day side of this planet, perpetually facing its nearby star, reaches temperatures of nearly 2,400 degrees Celsius, hot enough to vaporize iron into atmospheric gas. Powerful winds carry this iron vapor around toward the night side, where temperatures drop enough for the metal to condense back into liquid droplets. These droplets fall through the atmosphere as rain made of molten iron, a precipitation pattern completely unlike anything possible on any world in our solar system. The detection of this iron rain came through careful spectroscopic analysis of light passing through the planet's atmosphere during transit observations made from Earth-based observatories. Astronomers noticed that iron absorption signatures appeared strongly on the evening terminator, where day transitions to night, but were absent from the morning terminator on the opposite side. This asymmetry makes sense if iron vapor carried from the day side condenses and falls before reaching the morning side, depleting the atmosphere of iron in the regions where it would be returning to face the star again. The observation represents a remarkable achievement in reading subtle details about weather patterns on a world nearly 640 light-years away. JWST-121b presents another extreme example, a world so hot that its atmosphere actually glows, emitting light rather than merely absorbing and re-radiating the energy it receives from its star. Water molecules in the upper atmosphere reach temperatures where they emit infrared radiation directly, creating what scientists call a thermal inversion layer, where the atmosphere gets hotter with increasing altitude rather than cooler. This inverted temperature structure differs dramatically from Earth's lower atmosphere, where temperature generally decreases as you rise through the air toward colder upper regions. The physics creating this inversion involve complex interactions between atmospheric chemistry, and intense stellar radiation that scientists continue working to understand fully. The planet's atmosphere also contains vanadium oxide and titanium oxide, compounds that absorb stellar radiation efficiently and help maintain the unusual temperature structure observed in spectroscopic measurements. These molecules act somewhat like the ozone in Earth's stratosphere, absorbing incoming radiation and warming the layers where they concentrate, rather than allowing that energy to penetrate deeper. On WSP-121b, however, the scale and intensity of this process far exceeds anything in our solar system, creating temperature differences of hundreds of degrees between atmospheric layers. The world serves as a natural laboratory for studying atmospheric physics under conditions impossible to create artificially. WSP-33b adds another dimension of strangeness by orbiting a pulsating variable star that rhythmically brightens and dims over periods of just a few hours. The host star belongs to a category called delta Scuti variables, stars that oscillate in size and brightness as internal pressure waves travel through their interiors. The planet itself is a hot Jupiter, receiving intense and constantly varying radiation from this unstable stellar companion, creating conditions that change on timescales of hours rather than days or seasons. Astronomers have detected the signature of aluminum oxide in its atmosphere, another metal compound existing as gas under these extreme thermal conditions. HAT-P7b demonstrates that even clouds can become exotic under extreme exoplanet conditions, with observations revealing weather patterns involving clouds made of corundum, the mineral that forms rubies and sapphires. The day side of this planet reaches temperatures where corundum remains vaporized, while the slightly cooler night side allows this mineral to condense into cloud droplets that catch the light of the distant star. Observations over time have shown these clouds shifting across the planet's face, moving from the night side toward the day side and back again in observable weather patterns. The winds that drive these patterns blow at thousands of kilometers per hour, creating constantly changing conditions across this scorched and jeweled world. WSP-18b faces a fate that many close-orbiting exoplanets will eventually share, a gradual spiral inward that will eventually send it plunging into its host star within the next million years or so. The gravitational interaction between planet and star creates tidal forces that gradually transfer orbital energy, causing the planet to drift closer with each passing orbit around its stellar companion. A million years sounds like an enormous span of time by human standards, but represents merely an eye blink in cosmic terms, shorter than the time since our ancestors first developed stone tools. We are observing this planet during the final fraction of a percent of its total existence, a world whose doom is already certain, even if the actual end lies far in our future. 55 Cancri e orbits so close to its host star that surface temperatures likely exceed 2,000 degrees. Hot enough that significant portions of the surface may exist as vast lakes or oceans of molten rock. This super-Earth, roughly twice the size of our planet, completes one orbit in just 18 hours, meaning a full year passes before a single Earth day finishes. The extreme proximity to its star means one face likely remains perpetually turned toward that blazing sun, a day side of liquid magma, while the night side cools to merely red-hot temperatures. Recent observations suggest the planet may have an atmosphere despite these extreme conditions, though its composition remains uncertain. Kelt 9b loses mass so quickly that it creates a visible tail of escaping atmosphere, stretching behind it through space, material stripped away by the intense radiation of its blue host star. This mass loss occurs at rates of billions of kilograms per second, though the planet contains so much material that this process would require billions of years to completely erode away the entire world. The escaping gas includes hydrogen, helium, and heavier elements all flowing outward into space, creating a continuously replenished stream of planetary atmosphere, feeding into the stellar environment. Observations of this mass loss provide insights into processes that may have shaped the atmospheres of many other planets earlier in their histories when their stars burned more energetically. TOI 849b represents perhaps the strangest outcome of extreme conditions, a world that appears to be the exposed core of what was once a gas giant planet before its thick atmosphere was somehow completely removed. This Neptune mass object is incredibly dense, suggesting a composition of rock and metal that would normally lie buried beneath thousands of kilometers of atmospheric gas in a typical gas giant. Scientists debate whether this atmosphere was stripped away by extreme stellar radiation, blasted off by a giant impact, or perhaps never fully accumulated during the planet's formation. Whatever the cause, we observe a world that reveals planetary interiors normally hidden from view, a glimpse beneath the cloud tops to the dense heart of a giant world. The third part of our journey has explored the hottest and most extreme environments found among known exoplanets, worlds where familiar substances behave in unfamiliar ways, under conditions beyond earthly experience. Iron rains from alien skies, sapphire clouds drift on 1,000-kilometer-per-hour winds, and worlds spiral slowly toward fiery destruction in the embrace of their stars. These extreme cases push our understanding of planetary physics and atmospheric chemistry, serving as natural laboratories for studying processes that no Earth-based experiment could ever replicate. Yet even these scorching worlds represent only one flavor of exoplanetary strangeness. And our journey continues toward realms where chemistry itself takes unfamiliar forms. The assumption that rocky planets contain the same general mix of elements as Earth turns out to be far too narrow when considering the full range of worlds that might exist throughout the galaxy. Carbon planets represent a theoretical class of world where carbon rather than oxygen dominates the chemistry, creating geological and mineralogical conditions completely unlike anything in our solar system. On such a world, the rocks underfoot might be graphite rather than silicate. Mountains might be formed of diamond compressed under geological pressures. And the very concept of familiar minerals would need complete revision. Scientists believe such worlds could form around stars with different chemical compositions than our Sun, where carbon outnumbers oxygen in the primordial material. 55 Cancri E has been proposed as a possible carbon planet candidate, with some models suggesting this super-Earth might contain vast quantities of diamond formed under the extreme pressures inside its interior. The planet orbits a star with a higher carbon-to-oxygen ratio than our Sun, potentially providing the raw materials for carbon-dominated chemistry during planetary formation billions of years ago. If these models are correct, a significant fraction of this planet's total mass might consist of crystalline carbon, diamond compressed into existence by the weight of overlying layers. The extreme surface temperatures complicate any simple picture, likely creating conditions where diamond and graphite interact in ways we cannot easily predict. PSR J1719 to 1438b presents an even more extreme example. A planet orbiting a pulsar that appears to consist almost entirely of crystalline carbon at densities far exceeding anything possible on Earth. This world is actually the compressed remnant of a star that once existed as the companion to the pulsar, stripped of its outer layers and crushed into an ultra-dense sphere of carbon by gravitational forces during the system's violent history. The resulting object contains roughly 5 times Earth's mass, packed into a volume smaller than Earth itself, with density so extreme that the carbon has crystallized into what is essentially a giant diamond floating through space. The journey from normal star to diamond planet involved billions of years of stellar evolution and gravitational interaction. Carbon planets would have entirely different geology than worlds like Earth, with graphite forming the equivalent of our common surface rocks, and different minerals entirely filling the roles played by silicates. Mountain ranges might appear dark, rather than the browns and greys we associate with rocky terrain, composed of layered graphite rather than compressed seafloor sediments or volcanic material. Rivers might flow through valleys carved from pure carbon, though the exact chemistry of such a world's surface would depend on what atmosphere and temperature conditions exist. The concept challenges us to imagine planetary environments where even the most basic assumptions about rocks and minerals no longer apply. Hot Jupiter atmospheres reveal chemistry impossible in any planet from our solar system, with titanium oxide existing as atmospheric gas at temperatures that keep this compound from condensing into the white powder we use in paint and sunscreen. The same molecule that makes paint opaque floats through alien skies as vapor, contributing to the opacity and thermal structure of atmospheres heated to stellar temperatures. Vanadium oxide joins this exotic mixture on some of the hottest known worlds. Another compound we associate with solid industrial applications existing as gas under conditions no earthly furnace could maintain. These metal oxide gases absorb and emit radiation in ways that shape the entire temperature structure of the atmospheres they inhabit. HAT P7b reveals that even familiar minerals can form under conditions that create results almost unimaginable on Earth, with clouds of corundum drifting through an atmosphere heated by intense stellar radiation. Corundum is the mineral that forms rubies and sapphires, depending on trace impurities that give it color, one of the hardest natural substances, and typically requiring extreme geological conditions to crystallize. On this distant world, the temperatures are high enough that corundum exists as vapor on the day side, condensing into clouds only when carried by atmospheric winds to the cooler night hemisphere. The night side of this planet might feature ruby rain falling through skies painted in colors no human eye has ever witnessed directly. WASP 121b adds vanadium oxide to the list of exotic atmospheric constituents detected on ultra-hot gas giants, a compound that creates unusual temperature structures by absorbing stellar radiation high in the atmosphere. The vanadium oxide layer acts similarly to ozone in Earth's stratosphere, warming the upper atmosphere by absorbing incoming radiation before it can reach lower levels. This creates the thermal inversion observed on this planet, where temperatures increase with altitude in the upper atmosphere rather than decreasing as they do in Earth's troposphere. The chemistry operating in these extreme environments provides tests for atmospheric models that will eventually be applied to more Earth-like worlds. Kepler-10b demonstrates that extreme density does not require exotic chemistry, merely the concentration of heavy elements into a compact planetary body through normal processes taken to unusual extremes. This small rocky world, among the first confirmed rocky exoplanets ever discovered, is roughly twice as dense as Earth, despite being only slightly larger in diameter. The extreme density suggests a composition very rich in iron and other heavy metals, possibly a planet that formed from material already enriched in dense elements, or that lost lighter surface layers through some early catastrophic process. Walking on such a world, if the temperatures permitted standing rather than vaporizing, you would experience surface gravity significantly stronger than Earth's due to the concentrated mass beneath your feet. Some theoretical models predict exoplanets, where the entire atmosphere consists of vaporized rock, silicate compounds heated to temperatures where stone itself becomes gas and rises into the atmosphere. Such worlds would exist only around the most extreme close-orbiting planets, where surface temperatures exceed the melting and then boiling points of common rock-forming minerals. The weather on such a world might include periodic condensation of rocky material into clouds, followed by precipitation of molten droplets that fall back toward the magma ocean surface below. The concept sounds impossibly alien, yet follows directly from physical laws applied to conditions more extreme than any solar system planet experiences. HD 149026b possesses an unusually massive core of heavy elements, roughly 70 Earth masses of material, denser than hydrogen and helium, packed into its interior. Most gas giant planets contain far less heavy element material relative to their hydrogen and helium envelopes, making this world's composition genuinely unusual among known giant planets. The mechanism that created this heavy element concentration remains debated, with possibilities including formation in a region unusually rich in rocky material or accumulation of multiple smaller bodies during the system's early history. Whatever the cause, this planet's interior differs fundamentally from Jupiter's or Saturn's, with proportionally far more rock and metal hiding beneath its visible cloud tops. Some water worlds may contain exotic ice phases in their deep interiors, forms of ice that only exist under pressures so extreme that water molecules are forced into crystalline arrangements, impossible under normal conditions. These exotic ice phases, with names like Ice 7 and Ice 10, remain solid at temperatures far above the freezing point of ordinary ice, because pressure prevents the molecules from moving freely, despite their thermal energy. A deep water world might have layers of this hot ice separating a liquid ocean from a rocky core below, creating a planetary structure completely absent from any world we have directly explored. The concept of ice that remains frozen at hundreds of degrees challenges our everyday intuition about these familiar substances. The fourth part of our journey has explored the strange materials and exotic chemistry found on worlds where familiar substances behave in unfamiliar ways and unusual elements dominate the geology and atmosphere. Diamond planets, ruby clouds, iron rain, and rock vapor atmospheres represent just some of the possibilities that emerge when planetary conditions push beyond the narrow range experienced in our solar system. These exotic compositions remind us that Earth represents only one possible outcome among countless variations that planetary formation can produce throughout the cosmos. Our journey continues now towards systems where not one, but multiple suns illuminate the skies of orbiting worlds. The iconic image of twin suns setting over a desert landscape captured imaginations long before astronomers could confirm whether such worlds actually existed anywhere beyond the realm of cinematic invention. Kepler-16b provided that confirmation in 2011, becoming the first planet proven to orbit two stars simultaneously in what scientists call a circumbinary configuration. This Saturn-sized world circles both stars in a binary system roughly 200 light-years from Earth, completing one orbit every 229 days, while both stars themselves orbit each other in a much tighter inner dance. The discovery transformed speculation into observation, proving that stable planets could exist in the gravitationally complex environment of a double star system. Standing on a hypothetical moon orbiting Kepler-16b, you would watch two suns of different sizes and colors moving across the sky in intricate patterns determined by the orbital mechanics of the entire triple system. Sometimes both stars would set together in a double sunset, their combined light fading as they dipped below the horizon in sequence, or simultaneously depending on orbital geometry. Other times, one sun might set while the other remained above the horizon, creating periods of partial daylight with different colored illumination than the full brightness of both stellar companions. The shadow cast by any object would shift and split as the two light sources moved independently across the alien sky throughout each complex day. Kepler-47 represents an even more remarkable discovery, a system where multiple planets orbit a pair of stars, demonstrating that entire planetary systems can develop and persist around binary star pairs. At least 3 planets circle this binary, creating a miniature solar system where the central sun is actually 2 stars orbiting each other, while planets orbit both of them together. The orbits remain stable despite the gravitational complexity, because the planets orbit far enough from the central binary that the 2 stars effectively act as a single gravitational source. This architecture suggests that planet formation around binary stars may be common throughout the galaxy where suitable conditions exist. Some planets in binary star systems take a different approach, orbiting just one of the 2 stars, while the second star circles much farther away as a distant companion. These S-type orbits, named for the single star the planet immediately orbits, experience the second star as a very bright point in the sky, rather than a true local sun, providing comparable illumination. The gravitational influence of the distant companion star might cause subtle long-term changes in the planet's orbit over millions of years, but day-to-day experience would differ little from orbiting a single star. Alpha Centauri, our nearest neighboring star system, is actually a triple star system where planets might theoretically orbit individual stellar components in arrangements like these. HD 131399AB experiences something even more complex. Orbiting within a triple star system where 3 gravitationally bound stars create lighting conditions unlike any single or double star arrangement. The planet orbits one of the three stars at a distance of about 80 astronomical units, far enough that its orbital period lasts roughly 550 Earth years for a single journey around its primary sun. The other two stars in the system orbit each other as a close pair, appearing from the planet's perspective as a double star wandering slowly across the sky over decades. During certain seasons lasting centuries, all three stars would appear above the horizon simultaneously, casting three distinct shadows of different intensities and colors. Celt 4AB adds yet another layer of complexity. A hot Jupiter orbiting within a quadruple star system where four gravitationally bound stars create a hierarchical arrangement of binary pairs. The planet orbits the primary star of the system, while a second star orbits that primary at moderate distance, and two additional stars orbit each other as a pair orbiting the whole inner arrangement. From the planet's perspective, 3 points of light, in addition to the primary sun, would trace paths across the sky, though the more distant pair might appear as a single bright point given their separation. Such complex stellar environments were once thought unlikely to host planets at all, making discoveries like this one surprising evidence that planet formation succeeds, even in chaotic gravitational conditions. Binary star planets experience seasons and climate patterns completely unlike anything on Earth, where our single sun creates simple yearly cycles based on axial tilt rather than multiple moving heat sources. The varying distance between a planet and two independently moving stars creates temperature variations on timescales determined by the stellar orbital periods, rather than the planet's own axial orientation. A circumbinary planet might experience warmer and cooler periods as the two stars come together and move apart relative to the planet's orbital position, adding complexity to any seasonal patterns. Climate modeling for such worlds requires tracking multiple moving heat sources whose positions relative to each other and to the planet constantly change throughout each orbit. Some binary star systems create regular eclipse patterns visible from any planets orbiting within the system, as the two stars periodically pass in front of each other from certain viewing angles. Kepler-16's two stars eclipse each other regularly, creating measurable brightness variations that helped astronomers detect and characterize the system long before the circumbinary planet was discovered. From Kepler-16b's perspective, these eclipses would appear as one star passing in front of the other, temporarily dimming the combined illumination reaching the planet's surface for a few hours. The predictable rhythm of these eclipses might create regular variations in light and temperature noticeable to any hypothetical observers watching their binary suns. Circumbinary planets tend to be gas giants rather than small rocky worlds, likely because the gravitational dynamics of forming and maintaining stable orbits around two stars favor larger, more massive planets. The same gravitational complexity that makes these systems interesting also makes them challenging environments for small planets to survive long-term without being ejected or destabilized by the moving stars. Gas giants with their greater mass can maintain stable orbits more easily, though examples of smaller circumbinary planets likely exist and await discovery with more sensitive instruments. The bias toward finding larger planets may partly reflect our detection capabilities rather than the true population of worlds orbiting binary stars. The abundance of binary and multiple star systems throughout the galaxy suggests that multi-sun planets may actually be quite common. potentially rivaling single-star planets in total numbers across the Milky Way. Approximately half of all Sun-like stars exist in binary or multiple star systems, rather than as isolated singles like our own solar system's central star. If planets form around a significant fraction of these systems, then worlds with multiple suns in their skies might outnumber worlds like Earth with our simple single-star arrangement. The universe's diversity of planetary environments extends to the very nature of the suns that warm these worlds and light their skies. The fifth part of our journey has explored the complexity and beauty of worlds illuminated by more than one sun, from classic twin sun systems to quadruple star arrangements hosting hot Jupiter planets. These multi-star systems challenge our single-sun assumptions about planetary environments, while demonstrating that planets can form and survive in gravitationally complex settings throughout the galaxy. The interplay of multiple light sources creates visual experiences and climate patterns impossible on any world orbiting a lone star like our Sun. Our journey continues now to examine what we have learned about the atmospheres that wrap around these distant worlds, revealed through light that carries their chemical secrets across the void. The wind screaming around HD 189733b reaches speeds of approximately 8,700 kilometers per hour, measured directly through observations of how atmospheric gas moves relative to the planet as a whole. This hot Jupiter orbits so close to its star that one side permanently faces the searing heat, while the other side remains in perpetual darkness, creating temperature differences that drive atmospheric circulation of almost unimaginable intensity. The atmosphere tries to redistribute heat from the permanently blazing day side to the eternally dark night side, driving winds that exceed any storm ever recorded in our solar system by enormous margins. Even Jupiter's Great Red Spot, one of the most powerful storm systems known, produces winds only a fraction as strong as the steady circulation patterns on this distant world. These extreme winds were detected through a technique that measures how different parts of the planet's atmosphere move toward or away from Earth as the planet rotates and circulates. Gas moving toward us shifts light toward bluer wavelengths, while gas moving away shifts light toward redder wavelengths, an effect called Doppler shifting that allows precise measurement of motion across interstellar distances. By carefully analyzing how these shifts vary across the planet's visible face during transit, astronomers could map wind patterns and determine that atmosphere flows from dayside to nightside at these remarkable speeds. The measurement represents one of the most direct detections of weather patterns on any world beyond our solar system. WSP-39b provided the clearest early spectrum of carbon dioxide in any exoplanet atmosphere, detected by the James Webb Space Telescope within months of beginning scientific operations in 2022. The molecule appeared as a distinctive absorption feature. At wavelengths around 4.3 microns in the infrared, exactly where carbon dioxide is expected to leave its fingerprint, based on laboratory measurements here on Earth. This detection confirmed that JWST could identify specific atmospheric components on distant worlds with sufficient precision to distinguish between different possible compositions. The same planet later yielded detections of water, carbon monoxide, sodium, potassium, and photochemically produced sulfur dioxide, becoming one of the best characterized exoplanet atmospheres to date. The presence of carbon dioxide on WSP-39b reveals something important about the planet's formation history and the conditions that prevailed when this world accumulated its massive atmosphere billions of years ago. Carbon and oxygen atoms must have been present in the primordial disk of material surrounding the young star, incorporated into the planet's atmosphere as it grew larger and pulled in surrounding gas and dust. The ratio of carbon dioxide to other molecules provides clues about temperatures and pressures during formation, allowing astronomers to work backward from current observations to ancient conditions. Each molecule detected adds another piece to the puzzle of how this world came to be. WSP-96b revealed remarkably clear atmospheric conditions, with water vapor absorption features standing out sharply against the background spectrum, without the muting effects of high-altitude clouds or hazes. Many hot Jupiter atmospheres contain thick cloud layers that partially block transmission of starlight, reducing the strength of molecular signatures and making composition determination more difficult. The relative clarity of WSP-96b's atmosphere allowed detection of water with unusual precision, demonstrating what becomes possible when viewing conditions cooperate with observational capabilities. The resulting spectrum became one of JWST's iconic early images, showing exactly what the telescope was designed to achieve. Some hot Jupiter atmospheres exhibit temperature inversions, where the upper atmosphere is actually hotter than the layers below it, completely reversing the normal relationship seen in Earth's troposphere. These inversions occur when atmospheric components absorb stellar radiation efficiently at high altitudes, warming those regions before the energy can penetrate to deeper layers below. Titanium oxide, vanadium oxide, and other metal oxides have been proposed as the absorbers responsible for creating these unusual temperature structures on the hottest known exoplanets. Understanding these inversions helps astronomers interpret spectra correctly and determine what molecules are present at different atmospheric depths. GJ 1132b offers a tantalizing glimpse at how planetary atmospheres might regenerate after being stripped away by intense stellar radiation during a star's more active youth. This rocky super-Earth may have lost its original atmosphere early in its history, when its red dwarf host star flared more frequently and intensely than it does today. Volcanic activity might now be slowly rebuilding an atmosphere from gases released from the planet's interior, creating a secondary atmosphere distinct from whatever primordial envelope the world originally possessed. If confirmed, this process suggests that atmospheric loss does not necessarily mean permanent atmospheric absence. HD 82606b experiences the most extreme temperature swings known on any exoplanet. Its highly elliptical orbit carrying it from close approach to its star out to much greater distances in a cycle lasting about 111 Earth days. As the planet swings through closest approach, its atmosphere heats by roughly 700 degrees Celsius in just a few hours, driven by the intense radiation received during these brief passages near the stellar surface. The rapid heating creates dramatic atmospheric expansion and violent weather patterns that then gradually calm as the planet recedes to cooler distances over the following weeks. Scientists have modeled what storms might look like during these extreme heating events, predicting supersonic winds and rapidly forming cloud patterns unlike anything in our steadier solar system. Some Exoplanet atmospheres glow visibly on their night sides, emitting thermal radiation from gas so hot that it radiates in infrared wavelengths, detectable across interstellar distances, even without illumination from the host star. This thermal emission allows study of night-side conditions that would otherwise remain completely hidden from view, providing information about how heat distributes across planets with permanent day and night hemispheres. The measurements reveal that some hot Jupiters transport heat efficiently from day to night sides, while others show dramatic temperature differences between hemispheres, suggesting differences in wind patterns and atmospheric circulation. Night-side observations complement day-side studies to build more complete pictures of atmospheric dynamics. JWST-43b demonstrates that atmospheric chemistry can vary dramatically between the permanent day and night hemispheres of tidally locked planets, with different molecular abundances detected on opposite sides of the world. The day side, constantly exposed to intense stellar radiation, hosts photochemical reactions that create or destroy certain molecules at rates that balance differently from the cooler night-side chemistry. As wind carries atmospheric gas from day to night and back again, the mixture of molecules changes with position around the planet, creating chemical geography in addition to temperature geography. These variations complicate atmospheric characterization, but also provide additional information about circulation and chemistry working together. The sixth part of our journey has explored the remarkable atmospheres revealed through careful observation of light passing through and radiating from distant worlds orbiting other stars. Supersonic winds, clear skies, temperature inversions, volcanic renewal, and extreme heating events all appear among the atmospheric phenomena detected on exoplanets throughout the galaxy. Each observation technique provides different information, combining to build increasingly detailed pictures of what conditions actually exist on these worlds we cannot yet visit in person. Our journey continues now toward realms where water dominates, ocean worlds, and ice-covered bodies where liquid depths might extend far beyond anything in our solar system. Kepler-22b may represent a true ocean world, a planet potentially covered entirely by water, with no land breaking the surface anywhere across its entire globe, depths extending perhaps hundreds of kilometers down. This super-Earth orbits within the habitable zone of its Sun-like star, receiving roughly the same amount of energy that Earth receives from our Sun, suggesting temperatures compatible with liquid water if an appropriate atmosphere exists. The planet is roughly 2.5 times Earth's diameter, large enough that its mass might include substantial water fraction, depending on how it formed and what materials accumulated during its assembly billions of years ago. Models suggest that if water comprises a significant percentage of this world's mass, the resulting ocean would exceed Earth's deepest trenches by orders of magnitude. Descending through the atmosphere of such a world, you would eventually reach a surface that is simply more water rather than any solid ground, waves stretching in every direction without any continent or island to break the monotony. The ocean would continue downward through regions where sunlight fades to complete darkness, through depths where pressure builds beyond anything experienced in Earth's oceans. At sufficient depths, the pressure would become extreme enough that water itself might compress into exotic ice phases that remain solid despite temperatures far above normal freezing. creating a layer of hot ice separating the liquid ocean from whatever rocky core might lie beneath. The structure of such a world would differ fundamentally from any planet or moon in our solar system. JWST shows spectroscopic evidence of water or water vapor in quantities suggesting this world might be an ocean planet, or at least a world with extremely water-rich composition. The planet is slightly smaller than Neptune, but likely much denser than the ice giants of our solar system, suggesting a rocky interior surrounded by substantial water layers rather than a typical gas giant atmosphere. Its spectrum shows muted features consistent with a steamy atmosphere thick with water vapor, potentially above a liquid ocean surface that has never experienced a glimpse of solid ground. The star it orbits is a red dwarf much cooler than our Sun, requiring the planet to orbit closer to receive adequate warmth for liquid water to exist. 2i 1452b orbits within a binary star system and appears to be a water world where water may comprise up to 30% of the entire planet's mass, compared to less than 1% for Earth. This proportion would create water layers extending thousands of kilometers deep, far surpassing any ocean depth possible on planets like Earth, where water accumulates in basins carved from solid, rocky surfaces. The planet resides in the habitable zone of its red dwarf primary star, receiving energy compatible with liquid surface water under appropriate atmospheric conditions. Recent observations have continued to refine our understanding of this distant world's properties, confirming its status as one of the most promising water world candidates discovered to date. K2-18b has received extensive attention for its confirmed water vapor atmosphere and its location within the habitable zone of its host star, making it one of the most intriguing potentially habitable worlds known. The James Webb Space Telescope detected not just water, but also carbon dioxide, methane, and possibly dimethyl sulfide, creating a chemical inventory that scientists are still working to interpret correctly. Some models suggest this world might be a Hycean planet, a type of world with a hydrogen-rich atmosphere above a global ocean, potentially hosting conditions suitable for life in its watery depths. The dimethyl sulfide detection, if confirmed, would be particularly significant since this molecule is produced primarily by marine organisms on Earth. TRAPPIST-1d appears to have lost enormous quantities of water over its history, with models suggesting this world may have lost the equivalent of 20 Earth oceans worth of water to space through photolysis and atmospheric escape. The intense ultraviolet radiation from its red dwarf star breaks water molecules apart in the upper atmosphere, allowing hydrogen to escape into space, while oxygen either escapes or becomes bound into surface minerals. This process has likely continued for billions of years, gradually drying out what may once have been an extremely water-rich world into whatever remains today. Whether any water survives on this planet's surface or in its atmosphere remains uncertain. LHS 1140b combines several favorable properties for potential habitability, including location in the habitable zone of a relatively quiet red dwarf star and density consistent with either a rocky composition or significant water content. The planet is about 6 times Earth's mass and sits close enough to Earth for detailed atmospheric study, with current and next-generation telescopes designed for characterizing small rocky worlds. Models suggest It might have either a rocky surface with a thick atmosphere or a water world configuration with oceans of significant depth. Though determining which scenario is correct requires observations beyond current capabilities, the relative quietude of its host star improves the chances that any atmosphere has survived intact, despite billions of years of exposure. Some water worlds may contain exotic ice phases in their deep interiors that challenge our intuitions about how water behaves under conditions never experienced on Earth. Ice 7 forms at pressures above about 30,000 times Earth's atmospheric pressure, maintaining a solid crystalline structure at temperatures that would melt ordinary ice instantly. At even greater pressures, Ice 10 and other exotic phases emerge, each with different crystalline structures and physical properties that scientists have studied in laboratory experiments designed to simulate planetary interiors. A deep water world might contain layer after layer of these exotic ices, separating liquid zones from each other in a structure unlike any world humans have directly explored. Proxima Centauri b, the closest known exoplanet to Earth, might possess a subsurface ocean, despite surface conditions that are probably too harsh for liquid water to exist exposed to the radiation environment of this active red dwarf star. Tidal heating from the planet's close orbit could maintain internal warmth, similar to how Jupiter's gravity heats the interior of its moon Europa, despite the freezing conditions on that moon's surface. A protective ice shell could insulate a liquid ocean beneath from the cold of space and the radiation of the nearby star, creating a potential refuge for liquid water. Whether such an ocean actually exists remains unknown, but the possibility makes Proxima b an even more intriguing target for future study. The TRAPPIST-1 planets may have exchanged water with each other throughout their shared history, through a process mediated by asteroid and comet impacts, delivering material between these closely spaced, sibling worlds. Impacts on one planet can eject material into orbits that eventually intersect other planets in the system, potentially transferring water ice or water-bearing minerals across the relatively short distances that separate these 7 Earth-sized worlds. If life ever arose on one TRAPPIST-1 planet, similar transfer mechanisms could potentially have spread it to neighboring worlds, creating the possibility of a connected biosphere spanning multiple planets. The compact nature of the system makes such exchanges far more likely than similar transfers would be across the much larger distances separating planets in our solar system. The 7th part of our journey has explored the ocean worlds and water-rich planets that represent some of the most intriguing targets in the search for potentially habitable environments beyond Earth. These watery realms range from global surface oceans to subsurface refuges hidden beneath protective ice shells, from confirmed water vapor atmospheres to theoretical exotic ice layers under extreme pressure. Water's importance for life as we understand it makes these worlds particularly compelling subjects for continued study and eventual closer investigation. Our journey continues now toward the loneliest destinations of all, the rogue planets that drift between the stars without any sun to call their own. Somewhere in the darkness between stars, untethered to any sun and warmed by no external light, worlds drift in solitude through the vast emptiness that separates stellar systems across the galaxy. These rogue planets have either been ejected from the systems where they formed or condensed directly from interstellar gas clouds without ever orbiting a star at all. beginning their existence alone. Estimates suggest that billions of such worlds may wander through our galaxy, possibly outnumbering the stars themselves, and representing a hidden population of planetary bodies invisible to most detection methods. They produce no reflected light because no star illuminates them, and only the faintest infrared glow from their slowly cooling interiors betrays their presence against the cold background of space. PSOJ 318.5-22 is a young rogue planet, only about 12 million years old, still glowing faintly in infrared light from the residual heat of its relatively recent formation. This world has roughly 6 times Jupiter's mass, making it large enough that some astronomers debate whether to classify it as a very low-mass brown dwarf rather than a planet. Though the distinction becomes blurry at these intermediate sizes, its youth means it has not yet had time to cool significantly, allowing detection through infrared observations that would miss older, colder rogue worlds that have radiated away their formation heat over billions of years. Within a few 100 million years, this object will cool enough to become invisible to our current instruments. Rogue planets retain internal heat for billions of years through the slow decay of radioactive elements in their interiors, maintaining warmth long after any residual formation heat has radiated away into space. This process, the same one that keeps Earth's interior hot enough for mantle convection and plate tectonics, continues regardless of whether a star provides external energy or not. A rogue planet with sufficient mass and radioactive material might maintain temperatures above the melting point of water in its deep interior for timescales comparable to the current age of the universe. The surface would be frozen solid by the cold of interstellar space. But kilometers below that icy crust, liquid water might persist in permanent darkness. Some scientists have proposed that rogue planets with thick hydrogen atmospheres might even maintain relatively warm surface conditions despite the absence of any stellar heat source to warm them. Hydrogen is an extremely effective greenhouse gas, trapping infrared radiation so efficiently that even the faint internal heat from radioactive decay could potentially maintain temperatures above freezing at the surface. Such a world would be completely dark, with no sun ever rising or setting, yet might harbor liquid water simply because its thick atmospheric blanket prevented that heat from escaping. The concept stretches our assumptions about what conditions habitability requires. The OGL survey, designed to detect gravitational microlensing events, where foreground objects briefly magnify background starlight, has revealed multiple candidate rogue planets drifting through the galaxy's interstellar regions. When a rogue planet passes between Earth and a more distant star, its gravity bends and focuses the background starlight, creating a temporary brightening that reveals the invisible wanderer's presence. These events last only hours to days, depending on the mass of the lensing object and its speed across our line of sight, requiring continuous monitoring of millions of background stars to catch the brief flickers. The technique has successfully detected rogue planet candidates ranging from Earth mass to Jupiter mass, though precise characterization remains challenging. Rogue planets may form through 2 distinct processes that lead to very similar outcomes despite completely different origins: ejection from existing planetary systems, or direct collapse from interstellar gas. Some worlds begin life in normal orbit around young stars, then get flung into interstellar space through gravitational interactions with other planets, passing stars, or the chaotic dynamics of the system's early evolution. Others may condense directly from small pockets of interstellar gas that collapse under their own gravity but lack sufficient mass to ignite stellar fusion, becoming free-floating planetary mass objects from the moment of their formation. Both pathways produce worlds adrift between the stars, indistinguishable from each other by any current observational technique. A rogue planet could theoretically pass through our solar system at some point in the future, though the vast distances between stars make such encounters extremely rare on human timescales. The gravitational influence of a passing rogue would depend entirely on how close it came and how massive it was, ranging from imperceptible effects to potentially catastrophic disruption of planetary orbits, if the passage were close enough. Astronomers have found no evidence of any rogue planet currently approaching our solar system, though detecting such objects remains challenging until they come close enough for gravitational lensing or direct infrared observation. The odds of a close passage occurring within any given century remain extremely small. The smallest detected rogue planet candidates have masses comparable to Earth, or even less, revealing that the population of free-floating worlds includes not just giant planets, but rocky worlds similar in scale to our own. Detecting such small objects requires exceptional observational luck, since their gravitational lensing signals are weaker and briefer than those produced by more massive rogue Jupiters, and require the rogue to pass very precisely between Earth and a background star. The handful of Earth mass candidates detected so far suggests that small rogues may actually outnumber large ones, following the same pattern seen among planets orbiting stars, where smaller worlds are more common than giants. The galaxy may contain trillions of Earth-sized worlds wandering between the stars. Rogue planets experience no day or night in any meaningful sense, only the unchanging darkness of interstellar space, where the nearest stars appear as bright points, no different from the countless others scattered across the sky. A hypothetical observer standing on a rogue planet's frozen surface would see the Milky Way stretching overhead in stunning clarity, uncontaminated by any nearby stellar glare, the combined light of billions of distant suns providing the only illumination. No sunrise would ever come to warm that frozen landscape, and no seasonal variation would ever break the monotony of eternal cold and darkness. Time would pass, marked only by the slow rotation of the sky as the rogue continued its endless journey through the void. If rogue planets can maintain subsurface oceans through radioactive heating alone, they might represent the most numerous potentially habitable environments in the galaxy, vastly outnumbering planets in conventional circumstellar habitable zones. Such habitats would be completely isolated from any stellar energy source, relying entirely on the planet's internal heat for whatever warmth life might require to persist. The darkness would be absolute, eliminating any possibility of photosynthesis or other light-dependent biology. Though chemosynthetic life forms might theoretically thrive near hydrothermal vents on the ocean floor, these hidden oceans might persist for billions of years, patient, dark refuges in the greater darkness between the stars. The eighth part of our journey has explored the solitary worlds that drift without suns through the spaces between stellar systems, carrying whatever internal warmth they possess into the endless cold of interstellar space. These rogue planets represent a hidden population of potentially billions of worlds, most completely invisible to our current detection methods, yet present throughout the galaxy in numbers that may exceed the stars themselves. Some may harbor liquid water beneath frozen surfaces, maintained by nothing more than radioactive decay in geological endurance of the surrounding darkness. Our journey continues now toward the remarkable systems where multiple planets orbit together, locked in resonances and arrangements that reveal how solar systems form and evolve. Kepler-90 holds a special place in exoplanet history, as the first system discovered to host as many planets as our own solar system. 8 worlds confirmed orbiting a single sun-like star roughly 2,700 light-years from Earth. The 8th planet was discovered in 2017 using machine learning algorithms trained to recognize planetary signals in data from the Kepler Space Telescope, demonstrating how artificial intelligence could accelerate the search for worlds hidden in vast datasets. All 8 planets orbit much closer to their star than Earth orbits the Sun, with even the outermost completing its year in just over 330 Earth days. The system resembles a compressed version of our solar system, as if Jupiter and Saturn had been pushed inward to orbit where Venus and Earth do. The innermost planet of Kepler-90, World B, completes an orbit in just 7 days, racing around its star more than 50 times for every single orbit the outermost planet completes in its wider path. The system demonstrates that planetary architectures can differ dramatically from the familiar arrangement of our home solar system, where inner rocky planets and outer gas giants maintain clear separation. In Kepler-90, small and large planets mix together in close quarters, all crowded into a region of space that would fit easily inside Earth's orbital distance from our Sun. How such a system formed and reached its current stable configuration remains an active area of research and continuing scientific debate among planetary scientists. The TRAPPIST-1 system achieves something even more remarkable than mere planet count. With all 7 of its Earth-sized worlds locked into a precise mathematical relationship called an orbital resonance chain, the orbital periods of adjacent planets form simple whole number ratios with each other, so that when the innermost planet completes 8 orbits, the next one completes 5 in the same span of time. This arrangement means that the planets repeatedly return to the same relative positions, gravitationally tugging each other in patterns that repeat and reinforce, rather than accumulating into chaotic instability. The system has apparently maintained this precise clockwork arrangement for billions of years since the planets first formed around their dim red dwarf star. Viewed from above the TRAPPIST-1 system, you would see 7 worlds tracing their paths around the small, cool star in coordinated motion. Like dancers following intricate choreography determined by gravitational forces. The innermost planet completes an orbit in just over 1.5 Earth days, while the outermost requires about 19 days for its longer journey. The entire system fits inside what would be Mercury's orbit around our Sun, a remarkably compact arrangement where neighboring worlds pass close to each other on astronomical scales. From any one of these worlds, sibling planets would be visible not as points of light, but as disks, showing phases like our Moon does. The proximity of the TRAPPIST-1 planets to each other means that surface features might be glimpsed from neighboring worlds under ideal conditions, a viewing experience impossible for any planet in our more spread-out solar system. Standing on TRAPPIST-1e, you might watch TRAPPIST-1f rise above the horizon as a disk large enough to show color and perhaps the faintest hints of atmospheric banding. The red dwarf sun would hang in the sky much larger than our sun appears from Earth, its ruddy light casting everything in warm orange and crimson tones throughout the endless day. This system offers perhaps the most visually dramatic planetary experience among all the known exoplanet systems catalogued to date. HR 8799 achieved fame through direct imaging, with 4 massive planets actually photographed in orbit around their star, their light separated from the overwhelming stellar glare through sophisticated instrumentation. These young gas giants still glow with the infrared warmth of their recent formation, bright enough to photograph despite the luminosity of their nearby star trying to drown out their faint signals. Time-lapse sequences, compiled from observations spanning years, actually show the planets moving along their orbits, providing direct visual confirmation that these points of light are indeed worlds circling their star. The orbits are enormous by solar system standards, with the outermost planet requiring approximately 460 years to complete a single journey around its stellar host. Watching the HR 8799 system evolve over years of observation provides something remarkable in exoplanet science: actual visible motion of worlds around another star captured in real images. The planets appear as faint dots arranged around the central star, each dot shifting position slightly from year to year as the worlds progress along their slow orbital paths. The innermost of the 4 giants orbits at roughly 14 times the Earth-Sun distance, while the outermost circles at about 68 times that distance, far beyond where Neptune orbits in our system. These wide separations and the system's relative youth combine to make it one of the best targets for direct imaging studies of giant planet atmospheres. Kepler-11 hosts 6 planets, all orbiting closer to their star than Mercury orbits our Sun, packed into a compact configuration that seemed almost impossibly crowded before Kepler revealed such arrangements are common. The planets range from about 1.5 to 4 times Earth's radius, making most of them larger than Earth, but smaller than Neptune, in a size range common among exoplanets. Planets in such compact systems interact gravitationally in ways that allow precise mass measurements from timing variations, providing information about planetary interiors otherwise impossible to obtain for isolated worlds. The measurements reveal that these planets have surprisingly low densities, suggesting thick gaseous envelopes surrounding relatively small solid cores beneath their visible cloud layers. Some planetary systems contain pairs of worlds sharing nearly identical orbits, a configuration called co-orbital that seems impossibly unstable until you understand the gravitational mathematics that can support such arrangements. 2 planets in a co-orbital configuration might trade places regularly, one moving slightly faster and catching up to the other, then gravitationally interacting in ways that swap their speeds. This cosmic dance can continue indefinitely, as long as the planets remain in the proper resonance, each approach and recession following the same pattern as countless predecessors before them. No confirmed co-orbital exoplanets have been discovered yet, but several candidate systems show hints of this exotic and fascinating arrangement. Planetary migration explains many of the unusual system architectures we observe today, where giant planets, apparently formed in the outer reaches of their systems, then spiraled inward over millions of years. The hot Jupiters discovered orbiting just days from their stars almost certainly did not form where we now find them, since temperatures that close to a star prevent hydrogen accumulation. Instead, they must have formed beyond what scientists call the frost line, where volatile gases could condense, then migrated inward through gravitational interactions with surrounding disk material. The migration process can also explain why some systems lack inner planets entirely, those worlds having been pushed into their stars or ejected during the giant's inward journey. The Upsilon Andromedae system shows evidence of past gravitational chaos in the current orbits of its planets, which follow highly elliptical paths, completely unlike the circular orbits in our solar system. These stretched orbits suggest that the planets experienced a period of strong gravitational interactions at some point in the system's history, possibly including ejection of planets no longer present. The surviving planets settled into their current eccentric orbits after this chaotic period ended, carrying permanent scars of their violent past in the shapes of the paths they trace. Many exoplanetary systems show similar signs of past instability, suggesting that the calm, orderly arrangement of our solar system may actually be somewhat unusual among planetary systems. Resonant chains, compact configurations, wide orbit giants, and chaotic eccentricities all appear among the thousands of known exoplanetary systems, demonstrating that no single template describes planetary formation. Our own solar system represents one outcome among many possibilities, and other arrangements may actually be more common throughout the galaxy, even if they seem exotic by our standards. Each newly characterized system adds another example to the growing catalogue of planetary architectures, testing theories of planet formation and dynamical evolution against the full diversity nature has produced. The universe appears far more creative in arranging planets than our single example could ever have suggested to astronomers studying only our immediate cosmic neighborhood. The ninth part of our journey has explored the remarkable variety of multi-planet systems that orbit other stars throughout the galaxy, from resonant chains locked in mathematical harmony to configurations bearing evidence of violent pasts. These architectures reveal how solar systems form, migrate, and evolve over billions of years, processes that shaped our own home system and continue reshaping systems throughout the cosmos. Each configuration teaches us something about the physics of planetary systems and the many paths that planet formation can follow from primordial disk to stability. Our journey continues now toward the oldest and youngest planets, worlds that have witnessed most of cosmic history and worlds still taking shape today. The oldest known planet in the universe formed roughly 12.7 billion years ago, just 1 billion years after the Big Bang itself. In an era when the universe was barely assembling its first generations of stars. This ancient world, designated PSR B162026b, orbits a pulsar in a globular cluster containing some of the most ancient stars in our galaxy, a relic population from earliest cosmic times. The planet has existed for nearly 3 times the age of Earth, witnessing most of the universe's history while our world was not even a theoretical possibility in any stellar nebula. If any process resembling life ever arose on this ancient world during its incomprehensibly long existence, it has had far more time to develop than anything on our young Earth. The host star of this ancient planet is actually two stellar remnants in a close binary relationship, a pulsar and a white dwarf orbiting each other, while the planet circles both in a wider path. The pulsar itself is the rapidly spinning remnant of a massive star that exploded as a supernova billions of years ago, now emitting beams of radiation like a cosmic lighthouse rotating many times per second. The planet somehow survived the supernova explosion that created the pulsar, either through fortunate positioning or because it formed later from debris left behind by the stellar death. Either scenario speaks to the resilience of planetary bodies and the ancient origins possible for worlds in extreme and violent environments. Imagining this ancient world requires stretching our sense of time far beyond comfortable human scales, contemplating existence across spans that dwarf the entire history of complex life on Earth. When this planet formed, the Milky Way galaxy was still taking shape, merging with smaller galaxies and accumulating the structure we see today when we look up at the night sky. Billions of years passed while stars formed and died throughout the cosmos, each generation enriching the universe with heavier elements forged in stellar cores and scattered through supernova explosions. Through all of this cosmic evolution, this single planet continued orbiting its stellar hosts, a silent witness to the universe's gradual transformation from primordial simplicity to present complexity. The very first confirmed exoplanets ever discovered also orbited a pulsar detected in 1992 through precise timing measurements of the pulsar's extraordinarily regular rotation that revealed gravitational perturbations. As planets orbit around the pulsar, their gravitational influence causes tiny shifts in the pulsar's position, which in turn cause tiny variations in the timing of radiation pulses reaching Earth. These variations, measured to nanosecond precision, revealed the presence of at least two planets, and possibly more, the first definitive evidence that planets existed beyond our solar system. The discovery surprised astronomers who had expected the first exoplanets to be found around normal stars like our Sun, rather than exotic stellar remnants. The first exoplanet discovered around a Sun-like star came in 1995 with the detection of 51 Pegasi b, a hot Jupiter orbiting its star in just 4 days and revolutionizing planetary science. Swiss astronomers Michel Mayer and Didier Queloz detected the planet through the subtle wobble it induced in its host star's motion, a gravitational tug-of-war causing measurable shifts in starlight. The discovery earned them the Nobel Prize in Physics in 2019, recognition of how fundamentally their work had changed our understanding of planets and our cosmic context. Before this discovery, we knew of only 9 planets, all in our own solar system. Today, we know of more than 5,000 across the galaxy. The announcement of 51 Pegasi b generated both excitement and skepticism, since a giant planet orbiting so close to its star contradicted everything astronomers thought they understood about planet formation. In our solar system, giant planets orbit far from the Sun, where temperatures allowed hydrogen and helium to accumulate during the early formative period of planetary assembly. A Jupiter-sized world orbiting closer than Mercury seemed impossible according to prevailing theories. Yet the data clearly showed a massive companion circling the star in just over 4 days. This single discovery forced a complete revision of planet formation theory and opened our eyes to the diversity of planetary systems throughout the cosmos. The first exoplanet transit observation came in 1999, when astronomers detected HD 209-458b passing directly in front of its star, blocking a tiny fraction of starlight. This observation confirmed that the planet actually existed and was not some artifact of detection methods, while also providing the first direct measurement of an exoplanet's physical size. The transit method would later become the most productive technique for finding exoplanets, eventually employed by the Kepler Space Telescope to discover thousands of worlds during its mission. HD 209-458b thus marked not only a single discovery, but the beginning of an entire approach to planetary detection that would transform the field. The oldest planets formed when the universe contained far less of the heavy elements that comprise rocky planetary material, primarily just hydrogen and helium, created during the Big Bang, with traces of lithium. Rocky planets like Earth require silicon, oxygen, iron, and other elements that could only exist after multiple generations of stars had lived, died, and scattered these elements into space. The most ancient planets were therefore likely gas giants made primarily of hydrogen and helium, or perhaps rocky worlds with very different compositions than modern planet formation producers. Chemistry and composition change over cosmic time, meaning the oldest planets differ fundamentally from worlds forming around young metal-rich stars today. Captain B orbits one of the oldest stars in our solar neighborhood, a red dwarf estimated at roughly 11.5 billion years old, predating the formation of our Sun by about 7 billion years. The star Captain's star is actually an interloper from a small galaxy that the Milky Way consumed long ago, carrying its ancient planets along as it merged into our galactic structure. If this world ever hosted life during its incomprehensibly long existence, that life has had billions of years more than Earth's biosphere to develop and potentially reach complexity we can barely imagine. Whether conditions ever permitted life on this ancient world remains unknown, a question we cannot yet answer from our distant vantage point. The first direct image of an exoplanet came in 2004 with the detection of 2M1207b, a young gas giant orbiting a brown dwarf star roughly 170 light-years away. The planet was visible in infrared images as a faint point of light near its host, its own thermal emission from residual formation heat, providing the detectable signal across interstellar distances. This achievement demonstrated that with sufficient technology and favorable targets, exoplanets could be directly photographed rather than merely inferred from indirect signals in stellar data. Today, direct imaging has revealed dozens of young giant planets, though smaller and cooler worlds remain beyond current imaging capabilities, awaiting future technological advancement. Young planetary systems, still in the process of formation, provide living laboratories for understanding how planets assemble from the disks of gas and dust surrounding newborn stars in stellar nurseries. The ALMA radio telescope has imaged numerous protoplanetary disks, showing gaps, rings, and spiral structures that indicate planets actively forming within the disk material surrounding their young stellar hosts. PDS-70b and PDS-70c are young gas giants, actually observed still accumulating material from their surrounding disk, caught in the act of planetary assembly that happened around our Sun invisibly 4.5 billion years ago. These observations test models of planet formation against direct evidence, refining our understanding of processes that shaped every planetary system throughout the galaxy. Watching a planet form in real time, even across the slow timescales of astronomical observation, connects us to the processes that created our own world and every other planet in the cosmos. The gaps in protoplanetary disks mark where young planets have cleared their orbital paths, sweeping up material and preventing it from reaching the inner system where smaller rocky worlds might otherwise form. Spiral arms in some disks suggest massive planets gravitationally stirring the surrounding material, creating density waves that propagate through the disk like ripples across a cosmic pond. These structures tell stories of formation in progress, processes we understand through theory, now confirmed through observation of systems still in their youth. The 10th part of our journey has explored the vast span of cosmic time covered by known exoplanets. From ancient worlds that have existed for nearly the age of the universe to young planets still accumulating material today. This temporal diversity reveals that planet formation has occurred continuously throughout cosmic history, beginning when the universe was young and continuing in stellar nurseries throughout the present-day galaxy. Each era of cosmic history has produced planets under different conditions, with different available materials, creating diversity that reflects the evolving chemistry of the universe itself. Our journey continues now toward the physical extremes of planetary diversity, the largest, smallest, densest, and most tenuous worlds yet discovered, orbiting distant stars. WST-17b spans a volume larger than Jupiter's, despite containing only about half as much mass, an inflation so extreme that this gas giant could theoretically float in water if an ocean large enough existed. The planet orbits so close to its star that intense radiation heats the upper atmosphere and causes it to expand to remarkable dimensions, creating what scientists call a puffy or inflated hot Jupiter. The mechanism behind this inflation is not fully understood, with various theoretical proposals attempting to explain how the planet maintains such a bloated configuration against the gravity trying to compress it inward. Whatever the explanation, WST-17b represents an extreme in the balance between planetary mass and planetary volume among confirmed exoplanets. Approaching such a world, you would watch the planet grow larger and larger in your field of view, its apparent size expanding beyond what its modest mass would suggest to any experienced observer. The outer atmosphere would fade gradually into the darkness of space without a sharp boundary. The tenuous upper layers so diffuse that defining exactly where the planet ends becomes philosophically challenging. Deeper within, pressures and temperatures would increase, but even the core regions would be less compressed than similar depths within Jupiter, despite comparable overall planetary scale. This puffy giant represents the extreme endpoint of atmospheric inflation, a world stretched to its physical limits by relentless stellar heating. Kepler-37b sits at the opposite end of the size distribution, one of the smallest exoplanets ever detected, with a diameter only slightly larger than Earth's moon and roughly 1/3 Earth's diameter. This tiny world orbits very close to its host star, completing one orbit in just 13 days, while being heated to temperatures far too extreme for any liquid water on its diminutive surface. Detecting such a small planet required the extraordinary precision of the Kepler Space Telescope, which could measure stellar brightness changes as tiny as a few tens of parts per million with sustained observation. The existence of such small worlds so close to the detection threshold suggests that even smaller planets exist abundantly, but remain beyond current observational capabilities. HAT P67b has a density lower than Cork, so diffuse and extended that its physical structure seems almost impossible for a gravitationally bound object to maintain against the inward pull of gravity. This super-puff planet, roughly twice Jupiter's diameter, but only about 1/5 its mass, represents the most extreme example of atmospheric inflation observed to date among all confirmed exoplanets in the catalogue. The mechanism keeping the atmosphere so extended against the persistent inward pull of gravity likely involves intense heating from the nearby host star, combined with slow cooling rates in the upper atmospheric layers. Studying such extreme examples helps scientists understand the physics of atmospheric structure under conditions far beyond anything found in our relatively sedate solar system. TOI 849b represents perhaps the strangest planetary remnant in the known exoplanet catalogue. What appears to be the exposed core of a gas giant, whose thick atmosphere was somehow completely stripped away. The object contains roughly 40 Earth masses of material packed into a volume smaller than Neptune, with density indicating composition of rock and metal rather than the hydrogen and helium that should dominate. How this core became exposed remains actively debated, with possibilities including extreme atmospheric stripping by stellar radiation, collision with another massive body, or incomplete formation that never allowed full atmospheric accumulation. Whatever the mechanism, we observe a world that reveals planetary interiors normally hidden beneath thousands of kilometers of opaque atmospheric gas. Imagining this naked core floating in space creates a strange mental image, a dense sphere of compressed rock and metal that once lay buried at the heart of a Jupiter-like giant, now exposed to the cosmos. The surface, if we can call it that, would be unlike anything familiar from rocky worlds in our solar system, composed of materials that only exist at the extreme pressures found deep within giant planet interiors. No atmosphere softens the harsh radiation environment or creates weather patterns across this exposed remnant, just bare compressed matter facing the vacuum of space, directly, without protective covering. This world offers a window into normally hidden realms, a glimpse of what lies beneath the cloud tops of giant planets throughout the galaxy. Superpuff planets challenge our understanding of how planetary atmospheres can be structured, with some worlds showing densities comparable to cotton candy, despite containing enough mass to generate significant gravitational attraction. These extremely low-density worlds typically orbit very close to their stars, receiving intense radiation that might help maintain their inflated states against gravitational compression, trying to shrink them down. The physical mechanism must somehow resist the planet's own gravity without allowing the atmosphere to simply escape into space entirely. A delicate balance that current models struggle to fully explain. Continued observation of these puffy planets may eventually reveal the missing physics needed to understand their seemingly impossible inflated structures. The largest known exoplanets approach the fuzzy boundary between planets and brown dwarfs. Objects that formed like stars from collapsing gas clouds, but never achieved enough mass to ignite sustained hydrogen fusion. Brown dwarfs can be up to about 80 times Jupiter's mass before they become massive enough to sustain the fusion reactions that power the Sun and other true main-sequence stars. Objects between roughly 13 and 80 Jupiter masses may burn deuterium temporarily, but lack the mass to sustain the hydrogen fusion that defines stellar identity over cosmic timescales. The boundary between large planets and small brown dwarfs depends partly on formation history rather than just mass, making classification of some borderline objects genuinely ambiguous. Rox's 42Bb contains approximately 9 times Jupiter's mass, approaching the maximum size that most astronomers are willing to classify as a planet rather than a brown dwarf or failed star. The object orbits a young binary star system, still surrounded by the disk of gas and dust from which it formed just a few million years ago. In cosmic terms, its mass falls into the range where classification becomes uncertain, since objects this massive may have formed through direct collapse, like a star, rather than through core accretion, like planets in our solar system. Whether to call such objects planets, brown dwarfs, or something else entirely reflects ongoing debates about what exactly defines a planet at the high mass extreme. Hot Jupiters often show radii substantially larger than expected, from models that do not account for the intense stellar radiation these worlds receive from their nearby host stars continuously. The incoming energy heats the outer atmosphere, causing it to expand, while internal contraction and cooling slow down from what would occur on a more distant, isolated world, receiving less stellar flux. The exact mechanism for transmitting this surface heating into the deep interior, where it can affect the overall planetary radius, remains an active area of research, with several competing proposals. Understanding this inflation helps astronomers interpret observations of hot Jupiter sizes and masses in terms of actual composition and internal structure hidden beneath the visible cloud layers. Kepler-10b packs more than twice Earth's density into a planet only slightly larger than Earth in diameter, suggesting a composition extraordinarily rich in iron and other heavy metallic elements. This scorching world orbits so close to its star that surface temperatures likely exceed 1,000 degrees Celsius, making any detailed surface observations impossible with current or near-future technology. The extreme density suggests this world may be composed primarily of iron, with little of the silicate rock that comprises most of Earth's mantle volume beneath our familiar crust. Such iron-dominated compositions might result from formation in regions particularly rich in metallic material, or from loss of lighter surface layers through some early catastrophic process. The extremes of planetary density span an enormous range, from worlds less dense than cork to planets denser than pure iron, reflecting the diversity of compositions and conditions possible throughout planetary formation. This range far exceeds anything found in our solar system, where densities cluster within a relatively narrow band, determined by the specific materials and conditions of our particular cosmic neighborhood. Each extreme teaches us something about the physics of planetary interiors, the processes that concentrate or disperse different materials, and the variety of outcomes possible from similar starting ingredients. The universe experiments with planetary structure in ways our single solar system could never have revealed to astronomers studying only our immediate cosmic surroundings. The 11th part of our journey has explored the extremes of planetary size, mass, and density, found among the thousands of known exoplanets scattered throughout our galactic neighborhood and beyond. From puffy worlds, less dense than Cork, to iron-dominated super-Earths, denser than any planet in our solar system. The range of physical properties discovered exceeds all expectations based on our limited local sample. Each extreme teaches us something about the physics of planetary structure, the processes that create and shape worlds, and the diversity that emerges from similar ingredients combined in countless different ways. Our journey concludes now with a view of the full catalogue, the statistics of what we have found, and the vastness of what remains waiting to be discovered. The count of confirmed exoplanets now exceeds 5,500 individual worlds, each one detected through careful observation and verified through rigorous scientific analysis to ensure real planets underlie the data. This number grows every week as new discoveries are confirmed and added to the official catalogue maintained by astronomers around the world, tracking humanity's expanding inventory of known worlds beyond our solar system. The pace of discovery has accelerated dramatically since the first exoplanets were detected in the 1990s. With space-based surveys finding candidates faster than ground-based facilities can confirm them through follow-up observation. Thousands more candidates await the confirmation observations that would add them to the official count of verified exoplanetary worlds. The Kepler Space Telescope, which operated from 2009 until its fuel was exhausted in 2018, found more than 2,600 confirmed planets and thousands of additional candidates under investigation. This single mission transformed exoplanet science from a field of individual notable discoveries into a statistical enterprise with enough examples to draw reliable conclusions about planetary populations across the galaxy. Kepler stared at a single patch of sky for years, waiting for planets to transit across their stars repeatedly, building up evidence through patience and precision impossible from the ground. The mission demonstrated that planets are common, perhaps even ubiquitous, around the stars of our galaxy wherever we look. Nearly every star in the Milky Way galaxy appears to host at least one planet, based on statistical analysis of detection rates and the known biases in our observational methods that favor certain planet types. Red dwarf stars, the most common type of star in the galaxy, seem particularly likely to host small rocky planets in or near their habitable zones, where liquid water might exist. Sun-like stars also appear to host planets commonly, though the specific rate and types of planets may differ from what orbits smaller, cooler stellar hosts throughout the galactic population. When we look up at the night sky, almost every point of light we see likely has planets orbiting it, a realization that has transformed our understanding of cosmic architecture. Imagine each star in the night sky not as an isolated point of light, but as the center of its own planetary system, some with single worlds and others with complex arrangements of multiple orbiting bodies. The familiar constellations take on new meaning when you consider that Orion's belt stars each likely host planets, that the bright stars of the Big Dipper illuminate their own collections of orbiting worlds. The sky becomes not just a scattering of distant suns, but a gallery of solar systems, each one different from our own, yet formed through similar processes operating throughout the cosmos. This perspective, impossible before the exoplanet era, now represents our best understanding of how the universe is actually constructed. The most common type of planet discovered so far is the super-Earth or sub-Neptune, worlds larger than Earth but smaller than Neptune, with no equivalent in our own solar system for direct comparison. These intermediate-sized planets appear around a remarkable fraction of all surveyed stars, far outnumbering both smaller Earth-sized worlds and larger giant planets in the detection statistics compiled from major surveys. Why our solar system lacks this apparently common planetary type remains an open question, possibly related to the specific conditions or history of our system's formation 4.5 billion years ago. We live in a solar system that may actually be somewhat unusual among the general planetary population filling the galaxy. Hot Jupiters, despite being among the easiest planets to detect due to their large sizes and short orbital periods, turn out to be relatively rare when detection biases are properly accounted for in statistical analysis. Only about 1% of Sun-like stars appear to host these close-in giant worlds, meaning the universe is not actually full of overheated gas giants, despite their prominence in early exoplanet catalogues. The early dominance of hot Jupiter discoveries reflected observational bias rather than cosmic abundance, since these worlds produce large detectable signals, even with less sensitive instruments available in early years. More sensitive instruments reveal the far more numerous smaller worlds that early surveys simply could not detect from their limited technological vantage points. The TESS mission continues surveying the sky from its orbital vantage point, searching for transiting planets around the nearest and brightest stars, with priority given to targets suitable for atmospheric follow-up study. Unlike Kepler, which stared at a single deep field, TESS surveys nearly the entire sky in overlapping sectors, building an all-sky catalogue of transiting planets around nearby stellar hosts, accessible for detailed investigation. The planets TESS finds tend to be closer and brighter than Kepler's discoveries, making them better targets for the detailed atmospheric characterization that the James Webb Space Telescope provides. The two missions complement each other, Kepler revealing planetary statistics and TESS identifying the best individual targets for closer and more detailed study. Future missions currently under development will push atmospheric characterization capabilities even further, eventually enabling detailed study of atmospheres around rocky planets in habitable zones of nearby stars where life might theoretically exist. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will employ a coronagraph capable of blocking starlight to directly image planets around nearby stars without stellar interference. The Plateau mission from the European Space Agency will search for transiting planets around bright stars, building on TESS's legacy with even greater precision in measuring planetary sizes and orbital parameters. The Habitable Worlds Observatory concept envisions a space telescope specifically designed to image Earth-like planets and search for biosignatures in their atmospheres. Dozens of confirmed planets already orbit within the habitable zones of their host stars, at distances where surface temperatures might permit liquid water to exist under appropriate atmospheric conditions. Protecting the surface. This number will continue growing as more sensitive observations reveal smaller worlds at greater distances from their stars, expanding the catalogue of potentially habitable real estate in our galactic neighborhood. Whether any of these worlds actually harbor life remains unknown, and may remain unknown for generations, waiting for technologies not yet invented to provide answers to questions humanity has asked for centuries. The search continues, with each new discovery adding context to our understanding of how common or rare life might be throughout the cosmos. The transit method has proven the most productive technique for finding exoplanets, responsible for the majority of confirmed discoveries through the characteristic dimming that occurs when planets pass between their host stars and our instruments. The method works best for close-in planets with short orbital periods, which transit frequently and produce larger signals relative to more distant, smaller worlds that transit rarely and briefly. Radial velocity observations remain essential for measuring planetary masses, complementing the size measurements from transits to determine densities and bulk compositions that reveal interior structure. Direct imaging, gravitational microlensing, and astrometric measurements add additional tools, each suited to different types of planetary systems and different scientific questions about planetary properties. The search for Earth's true twin continues as the ultimate prize of exoplanet science. A rocky world, the same size as Earth, orbiting at the same distance from a sun-like star, in a configuration precisely mirroring our own. No such world has been confirmed yet, though candidates exist that match some, but not all of these criteria, with varying degrees of similarity to our home world. Finding an exact analog would require detecting a small planet with a year-long orbital period around a star similar to our Sun, a challenging observation that pushes current technology to its limits. Such a discovery likely awaits future instruments designed specifically with this goal in mind, perhaps within the working lifetimes of astronomers beginning their careers today. The universe contains an estimated 200 billion stars in our galaxy alone, with current statistics suggesting most of these stars host planetary systems of some configuration around them. The total number of planets in the Milky Way galaxy likely exceeds the total number of stars, meaning hundreds of billions of worlds exist within the boundaries of our single spiral home galaxy. Beyond our galaxy, hundreds of billions of other galaxies each contain their own hundreds of billions of stars, and presumably their own countless planets orbiting those distant suns. The scale of what exists dwarfs what we have found by factors so large that our catalogue represents merely the first tentative steps into an essentially infinite realm of discovery. This slow journey through 100 facts about exoplanets has carried us from the nearest potentially habitable worlds to the farthest glimpses our instruments can currently provide across interstellar distances. We have visited scorching gas giants where iron falls as rain, frozen rogues drifting alone between the stars, ancient worlds older than most of cosmic history, and young planets still taking shape around their newborn stars. Each fact represents years of careful observation and analysis, thousands of scientists working across generations to reveal what exists beyond our small corner of the cosmos we call home. The stars continue shining, as they always have, but now we know that nearly every one of them illuminates its own collection of worlds, waiting quietly in the darkness. The catalogue will continue growing as long as human curiosity endures, and as long as our instruments improve to reveal what currently remains hidden in the vast spaces between the stars. New telescopes will find new worlds. New technologies will characterize atmospheres we can barely detect today. and future generations will know things about exoplanets that we cannot yet imagine asking about. For now, the 5,500 known worlds represent our first glimpse into a universe far richer in planets than the most optimistic astronomers dared to predict just a few decades ago. The cosmos is full of worlds, and we have only begun to explore them from our small blue planet, orbiting an ordinary yellow star in an unremarkable corner of the galaxy. The night continues outside wherever you are resting. The same stars visible from your window that astronomers study with instruments far more sensitive than human eyes could ever evolve to be. Some of those stars host worlds we have discussed tonight. Planets with iron rain and diamond cores, and oceans deeper than any on Earth, stretching down into darkness and pressure. Others host worlds we have not yet found, waiting for future surveys and future telescopes, and future scientists to add them to the growing catalogue of cosmic real estate beyond our solar system. Sleep comes when it will, and the universe continues its patient existence, whether we are awake to contemplate it or drifting through dreams of distant worlds, orbiting distant suns.